In this video, we are going to discuss significant figures. This is a topic that is very heavy on a series of rules. However, we'll get a lot of practice with this in each of our lab experiments that we conduct this quarter. So first, let's start with differentiating exact from inexact when we talk about numbers. An exact number results from counting objects. It can also be the definition of something. So I can count the number of fingers on my hand, and I'll have 10 fingers. I can count the number of toes on my feet. I'll have 10 toes. Nothing really changes that, and I can just count them. And that's an exact number. I can also have then definitions which we consider to be like conversion factors. So I can define 1 meter as 100 centimeters. And these would all be considered exact numbers, and we won't consider them as having significant figures. Now, an inexact number is something that's measured. And that's the key part about this, is that it's a measured value. And that means that if someone measured it, there was an observation. And if someone observed something, there's a chance that they made a slight mistake, or that it is, there's some uncertainty to that value. And so our significant figures will allow us to report a number and communicate our level of uncertainty to the reader. And this is really powerful when we need to report something that we're doing in lab or something that we're measuring that'll be used to determine a dosage of medication later on. And so here's some measurements: a measurement of length, a measurement of mass, and a measurement of volume. They were all made by a person, and so they are all inexact numbers. So let's look at an example of this. I know this is a large block of text, but it's a word problem that's describing baking muffins. So a recipe calls for 100 dried cranberries. You measure out 1.5 cups of flour and 1 cup of rolled oats and add it to the mixture. Now the recipe also calls for the addition of 0.5 cups of butter, but you don't use a measuring cup. Instead, you note that on the stick of butter you have in the fridge, 8 tablespoons equals 0.5 cups and equals 1 stick of butter. So you just add the whole stick to the mixture. So let's walk through A, B, C, and D and talk about if they're an exact or inexact number. If you'd like, you can pause this video now and try these on your own first, and then restart it to hear the rest of the lecture. So let's start with 100 cranberries. Here we go. 100 dried cranberries. Is this an exact or inexact number? Well, we won't weigh out the cranberries. We won't measure them by volume. To measure them, we're going to count them out. So this is a counting number. And that makes it exact. This means if we used 100 dried cranberries from the recipe in a calculation, we wouldn't use significant figures on that value, or it would have infinite significant figures. The next one is 8 tablespoons or 0.5 cups of butter. Is this an exact or inexact number? Well, our recipe, it says that we put in the whole stick, and that this information about the 8 tablespoons or 0.5 cups is coming from information on the stick of butter. And so we would call this a definition. The stick of butter is defined as 0.5 cups, so this will be an exact number. So then we have another one to look at. We've got 0.15 cups of flour and 1 cup of rolled oats. I'm going to draw your attention to a word here: measure. These are measured values that you're going to use, like measuring cups to determine the amount that you're adding. So these are inexact. And if you've ever baked muffins or cookies and have tried to measure out an exact cup or 1.5 cups of something, there is definitely a little bit of uncertainty in exactly what that is. Now, how many significant figures do the inexact numbers have in this? And now we'll walk through this. So a significant figure is just going to be usually any of the non-zero numbers. And so if I'm looking at 1.5 cups, my number has 2 digits in it. So I would say it has 2 significant figures. Whereas if I'm looking at 1 cup, I only have 1 number reported here, right? One digit. So I would say this is 1 significant figure. So significant figures, I think, are best explained in the process of taking a measurement. So we have measured numbers and numbers that are not measured, or inexact and exact. And our inexact numbers are going to have significant figures associated with them. And significant figures are really just the number of digits reported for a measurement. And this communicates how accurate your measuring device might be, or how to which decimal place your measuring instrument can actually measure. And the number of digits you report then tells someone the level of accuracy of your instrument that you used. And it gives them some more information about how an experiment was carried out or how a number was measured. So when you measure something like height or volume or temperature, you are going to need to know exactly how many digits to report. And our rules for this are you are going to report the numerical values to the marked line and then estimate 1 digit beyond that. So let's do this with an example because this makes a lot more sense in that way. So let's say I have a graduated cylinder filled with water and I have blown up this little piece right here so you can see it. I would measure my graduated cylinder from the bottom of my meniscus right here that the water makes. So right there. And so when I report this, I'm going to look at the numbers that I can count on the marked lines because it's very easy for my eye to be drawn to these lines right here. So I've got 3, and then I have 1, 2, 3, 4, and then on the 5th line it's 4. So each of these marks are 0.2. So I've got 3.2, 3.4, and 3.6. And it looks like my water comes somewhere between 3.4 and 3.6. So these numbers right here correspond to the observed numerical values of the marked lines. But now I got to estimate 1 digit beyond that. And my line goes somewhere in between these two. And so I'm going to try to report a number between 3.4 and 3.6. And so my estimated digit is going to be in the 100ths place. You know, that looks a little bit more than half. I might say that this is 3.55. It's halfway, it's a little more than halfway in between. And so here I have 3 significant figures that I would report. I have 1 estimated. Digit and 2 that can kind of be associated with a line in between this 3.4 and 3.6. And so altogether then, this is the number that I would report. I would report 3.55 milliliters, and now I have a measurement. And I have a measurement that's reported with correct significant figures. So now that we can report a measured value or an inexact number with significant figures, how do we interpret a number that's been reported to us? Well, if we're reading instructions, or we're reading someone's report on what they did in the lab, and they make a measurement that they report as 65.2 grams, so measurement of mass, we can immediately see that we have 3 significant figures, and we know that this last digit was estimated. So that tells me that this device that was measuring mass had markings that went 64, 65, 66, and it was a little bit bigger than 65 and a little bit smaller than 66. So here's my estimated digit. So that tells me a little bit about how accurate the measuring device might be. If I compare that to a mass measurement like this next to it that has 6 significant figures, I know that this measuring device was able to have markings at 255.33, 255.34, 255.35, and that my measurement fell somewhere in between these 2 markings. Now, if I was looking at these 2 and comparing them, and I wanted to know which was a more reliable number or a more certain number, I would probably choose this one because my device is able to actually read numbers out to more decimal places. And so this might be a more certain mass measurement. So we're now going to walk through what makes a significant figure and not a significant figure when we're interpreting a number that's reported. And first of all, it's important to note that any non-zero number that's reported will be significant. So anything that's 1, 2, 3, 4, 5, 6, 7, 8, 9, these digits are always significant figures. The zeros get a little tricky. So let's walk through our rules for that. So some zeros are placeholders, and they are not significant digits. And some zeros are measured, and they're part of our measurement, and so they are significant. And so here, the zeros that are measured, these are going to be significant figures. And our zeros that are placeholders, these are not significant figures. So let's start with our placeholders and look at a couple of examples. So zeros that come after a non-zero number but don't have a decimal place are just placeholders. So these right here just help us understand that we're thinking about a number that's on the order of 10,000. But there's only 2 significant figures in this number, the 5 and the 2. This number right here has some placeholder zeros as well. These are zeros that come before the non-zero number, even if there's a decimal place. And so here, these are just telling us that this is on the order of 0.01, or the thousandths place. And again, this number also has 2 significant figures. It's just our 2 non-zero numbers. Now, significant zeros can be recognized in a couple ways. One, they're going to fall in between 2 non-zero numbers. So my significant figures will always span the beginning of my number and end of my number where they're non-zero. So this one has 4 significant figures. These zeros that are sandwiched in between 2 non-zero numbers count as significant figures. We measured them. So zeros after non-zero numbers that have a decimal place are also significant. So in this example, where we have 0.0520, this 0 right here is a significant figure. And if I look at all of my significant figures together, my non-zero, I start at the beginning of my non-zero numbers, and I go to all of my trailing zeros. So I have 3 significant figures in this number. Now, these ones right here are just placeholders because they come before the non-zero number. So really with this one, that decimal place is the trick. A decimal place makes trailing numbers significant, but not preceding numbers. Or preceding zeros. So sometimes these measurements can be a little tricky in how you actually answer it. And this problem is intended to highlight one of these little tricky moments with significant figures and zeros. So I recommend that you hit pause and try this problem out on your own, and then rejoin us for the solution. So in this problem, we have a graduated cylinder that has only two markings at the 1000 and 2000 place. So we want to report the volume, and we want to report the volume with the correct significant figures. So that means we get to measure to the mark, and that looks like this one comes right to 2000, and we get to estimate one digit. Now, since our markings come every 1000 milliliters, then my estimated digit is right here in the 100ths place. So if I was going to report this value, I can see it's right on the line. That's great. So it's 2000, and I'm estimating that it's right on that line. So here's my estimated digit. I'm estimating a 0 because I think it's exactly 2000. So how do I report this? I have these two as significant figures, and these two zeros are placeholders. And the challenge is, how do I report this number so I let people know the difference between the two? I can't place a decimal place anywhere other than at the end, but if I place a decimal place here, then it means I would have 4 significant figures, and that's not right. I only have 2 significant figures, and this is where scientific notation comes in. It is going to help me report a number with the correct significant figures. So I have 2 significant figures. That would be 2.0. And if I represent 2000 in scientific notation, I would take this decimal place and go 1, 2, 3. So times 10 to the positive 3, because it's a large number. So now this number equals 2000, right? But I have reported it with only 2 significant figures, my measured digit and my estimated digit. So we'll use scientific notation to clearly communicate significant figures and allow our reader of our measurement to understand exactly how precise or accurate our instrument was. So one of the next challenges with significant figures is that when we report a number in that we measure, we oftentimes need to manipulate that number. If I measure mass and volume, I might use those to calculate density, but I would have to go through a calculation. In this case, we measured the number of miles and the number of hours it took to travel that number of miles, and we're trying to calculate our speed in units of miles per hour. So if we have 2 measured values or more measured values, and we are going to multiply or divide them, we want to be able to still report the correct number of significant figures. For us, that means we're going to report the least number of significant figures, because that will accurately communicate our greatest amount of uncertainty. We don't want to over-represent a number and say that we're more confident that more confident than we really are. So I have 4 significant figures measured for my mileage, or my miles, and I have two significant figures measured for time. So when I divide these two, I'm going to use my multiplication and division rules for significant figures. These state that I'll report the number of significant figures that matches the fewest significant figures in my calculation. Remember, these are only going to be for my inexact numbers. So I've got 4 on top, 2 on the bottom. I can only report two significant figures for my answer, which would be 63. I am now going to make sure I report this correctly when I'm reporting to, and take into account the next digit that I'm going to drop from my calculation. So the first digit dropped here is greater than 5. So this means I'm going to need to round my 63 up to 64, because 63.8 is closer to 64 than 63. So 64 becomes a more accurate representation of the number I measured. So I'll report two significant figures and I'll round up. So remember that if a number, the first digit to be dropped, or the number following your significant figures, is between 0 and 4, you drop the remaining digits without rounding up. But if it's between 5 and 7, you need to round up the last digit that was significant by adding 1 to it, as we did in this example right here. So unfortunately, we don't have one significant figure rule for algebraic manipulations. We've got two. Things will be different when you use addition and subtraction rules. We will use this rule primarily when we do degrees Celsius to Kelvin temperature conversions. Otherwise, most of our conversions will use multiplication and division, and will report the least significant figures. For addition and subtraction calculations, we report the answer to the least number of decimal places of our original measured values. Again, this is going to be the decimal places of our inexact numbers. So if I measure 10.11 kilograms and I need to subtract a measured value of 3.6 kilograms, I have one decimal place in my 3.6 number. So I'll carry out my complete subtraction calculation and I get something like 6.51. But I need to report just one decimal place. So I'm going to drop that one and report just 6.5. Now, since this 1 was less than 5, I'm going to keep this 5 the same and I won't round it up. So it's just 6.5 kilograms for my final answer, reporting to the least number of decimal places. Oftentimes, we will need to do a series of calculations rather than just one. And so here's just some guidance about how to approach those with significant figures. We need to, in general, in chemistry, we have the rule that we never round our digits to the correct number of digits until the very end of the calculation. This allows us to report things a little bit more consistently with less kind of differences between how two people might calculate the same number. And so we will need to perform the calculation and assess the significant figures at each step. Rather than rounding at each step, we will just place a line under our significant figures to show that, to keep track of them. And when we're performing calculations, we're going to use we'll go through order of operations for priority. So we've got parentheses first, then multiplication and division, then addition and subtraction. Oh, sorry, I forgot one in there. After parentheses is exponents. Then multiplication, division, addition, and subtraction. So in this problem right here, we have something in parentheses. So we'll do this first. We'll subtract 5.489, or we'll subtract 5.01 from 5.489. And that gives us 0.479 if we put this into our calculator. But I need to report to the least number of decimal places. And my 5.01 has 2 decimal places. So if I was just doing this calculation, I would stop here and round to 0.48. But I'm going to keep going and just underline this to remind myself that I have 2 significant figures here, or 2 decimal places. Now my next step is all multiplication. So I'm going to report the least number of significant figures in this next step. So if I plug this into my calculator, I'll get this long number. And I have 3 significant figures for this number, 4 significant figures for this, and remember, 2 significant figures for this value. So I'll report my final answer to 2 significant figures. Since my digit that is first dropped is less than 5, I do not need to round up. So try this practice problem on your own, and then come back and watch the solution to it. I'll take a pause. All right, so hopefully you've had a chance to try that. We're going to try to report the average of these 3 numbers with the correct significant figures. These were all measured values. So to take the average, I'm going to add 68.62 degrees Fahrenheit to my 100.884 degrees Fahrenheit, to 5.2 degrees Fahrenheit. And then I'll divide this by my number of measurements, which is 3. So looking at this, these are my inexact numbers. But my 3 was a counting number, it was exact. So to do this calculation, I'm first going to add everything in parentheses and then divide. So this is 2 steps, essentially. My first step, I'm going to use my addition and subtraction rule. And for my second step, multiplication and division rule for my significant figures. So when I add these up in my calculator, I get 174.704. And looking at my decimal places, I've got 2, 3, and 1. And so this is my least. So I'll report 1 decimal place. Now I'm not going to round. Instead, I'm just going to make a note with a line under this 7 that says this is my last significant figure in this number. So the next step is to divide by 3. And in this case, I have an inexact number on top. So here's my inexact number. And I have an exact number on the bottom of my calculation. So I will still use the least number of significant figures of my inexact numbers when I report my answer. But I will, let's do it down here, but I will not take this into account. So my least number of significant figures is going to come from this number right here. I'll have 4 significant figures that I can report. So I'm doing in a multiplication and division, so I use the rule, but this non-significant number or exact number won't have an impact based on the number of digits it has. And so when I divide this by 3, I get 58.234666667 in my calculator. And I've got 4 significant figures. So right here. And if I look at my first digit to drop, it's less than 5. So I do not need to round up. So this will be 58.23 degrees Fahrenheit, my average, reported with correct significant figures.